Enlist at Oxford University to study the topics of bar sagging and indicator droop. Mr. Crispin here once again, and welcome to my workshop. Now, what a great set of comments I got in the video titled Setting a Tool Post Grinder. It was very generous of you all to leave so many comments, and there were some very interesting topics raised, some of which have caused me to go away and do some thinking, and I've decided to come back. Just a moment. Decided to come back and do this little video on what I consider to be the 4 most interesting topics. Hopefully some of the topics I was able to answer in the comments, but for the remaining ones which require perhaps more detail, let's head over to the lathe. Point number 1 is quite a nice one to think about, and it is in relation to dressing the wheel. The question goes something along the lines of, why bother going to all the trouble of setting this spindle up when you're going to dress the wheel and therefore true it up anyway? Well, the answer is pretty much straightforward geometry. So I'm going to put the wheel on. I'm going to use a single point diamond to first of all dress it parallel. I will then use a top side angle to dress on the 7.125 degree angle, and then using a dressing stick I will dish the face of the wheel for clearance. That will give me a wheel that looks something like this when considered in 2D. Parallel portion, angled portion, dished face. Now when that is spinning, much like a milling cutter, the back relief here will run all the way to the extremity and it will describe a flat face as shown in green. So my spinning wheel will actually look like this. That is going to allow me to grind the angled portion in the centre, in there, and it will also allow me to grind the flat face. Now the argument is, why align the spindle when you're going to dress it? Well, dressing the wheel will true the periphery to the machine's axes. So when I run up and down here, fine, it'll true the wheel and get it square with that axis of the machine. When I run up and down here, yeah, the angle will go on true and it will be parallel with the axes. But what it will not correct is the angle that the face is presented at. When I true the wheel with the dressing stick, I'm going to get a periphery that describes a flat surface, and that flat surface needs to be parallel with this. Think back to the little demonstration I did on the milling machine considering the tramming of the head. If the head is out, you produce a dished surface feeding in that way with that error, or if you've got that error you produce an angle. Exactly the same is going on here. This face needs to come on square. If it's not, it's going to produce a dished surface, or if it's out this way, it's going to produce an angled surface, or a very shallow cone. So basically it has to be square because you cannot dress out those errors. Periphery, yes, fine, you can dress it out, but these errors cannot be dressed out. Point number 2 is the most involved, and this is the one that's caused me to do quite a bit of thinking. I was introduced in the comments to the term bar sag / indicator droop, and I was asked directly in one of them, was I aware of this? Now, from a general engineering point of view, I am of course aware that the longer something is, the more it sags of a given material, and also that if it's in the horizontal direction, it sags downwards. So yes, I'm aware of that. But this very specific topic around bar sagging and indicator drooping, no, it's not something I've had to contend with before, and it applies very specifically to the errors incurred when using an indicator that is rotating about the horizontal plane and the effects of gravity on that indicator and bar arrangement. So I'll take this one step at a time, and to begin I'll show you a little demonstration to explain the concept of indicator sag. Here is an indicator that is about to droop. It has drooped by ½ mil, and worse than that, it doesn't even quite return to 0. Clear indicator droop. What's happening? Well, the effects of gravity are acting on the bar, the mechanism, and with the weight of the indicator to not help the situation. When I go from here to here, you can see there is clearly quite an effect on the indicator's reading. Now imagine you are using that setup to try and get the centre of this spindle in line with this workpiece. You put the clock on here, you go up here, down here, okay, minus 0.1, back up to the top, oh it's plus 0.1, make a few adjustments, 0, oh okay, right, it's 0 down here as well now, double check, oh okay, yeah, it's 0 at the top, 0, 0, that must be bang on. Well, sorry, it's not. Let's refer to the clipboard to see why. Here is a pictorial of what we have just been looking at. Noga arm with drop clock, and you can imagine this thing is spinning round and it is drawn at the 12 o'clock and 6 o'clock positions. I have just established that this droops, so let's draw in the effects of this. On the top it's going to be drooping down, so it's going to sag down. The indicator should really be up here. That is where we might think it is. Equally down here the bottom arm is going to sag down again, meaning that the error this time is like this. So compared to what we might think is happening, this has sagged in both directions downwards. The results of that are the following errors. The 0 lands there on the top and the 0 lands there on the bottom, meaning that, let's say we were trying to align this centre with this centre, we actually end up high on this side because the arms have sagged, meaning that it works out with an error. Sorry, I apologise for whatever this is. Meaning that in reference to the centre line, this side is high. Now based on this, should I take the whole method I have shown and disregard it? Well, there are two very important points to make. Number one, I was not using this big heavy indicator, nor was I using a hydraulically locking multi-joint arm. What I was using was this very lightweight Starrett indicator and this rather stiff steel bar. Now let's repeat the experiment. Here, in its current setup, as held exactly ish horizontal, I have a reading of 0. Now let's go up to the ceiling. My coat pocket has got stuck on the lathe one moment. That is a reading of just under half a thou. So this is the setup pretty much with the same overhang as I was using, and as you can see it's a totally different animal to the drop clock on the Noga base. That was point 1. To illustrate point 2, let's have a look at the actual setup I was using. Right, this is somewhat of a reconstruction, although I've rotated the dial around so you can see what's going on, but basically I've set it up with a similar overhang to what I had in the video, which by the way is very handy because it allows me to put the dial there and then watch it all the way round. When you have a dial here, obviously you lose sight of it for quite a chunk of its rotation. Right, major point number 1 was the weight of the indicator and the mounting system. Major point number 2 is this. I am measuring in the vertical plane, not top and bottom. The plane affected most by gravity is of course this one, and therefore if you are sweeping around top and bottom you are going to see the full effects of whatever bar sag there happens to be. Measuring in the vertical plane, this is of course reduced because the effects of gravity are not manifesting themselves in the same direct way. Now, as a very unscientific experiment, let's bring the indicator in and get a 0 reading. And what I'm going to do is simulate the opposite effect of the gravity. So we know the gravity is pushing it down. I am going to attempt to apply a little bit of force underneath, roughly enough to lift the weight of the indicator and therefore cancel out the effects of gravity. Sounds rather important. So if I really push on it, that's definitely enough weight to lift the indicator less than half a thou. To explain how the effects of gravity acting on the horizontal plane are affecting a measurement on the vertical plane, let's refer to the clipboard. Much as before, I'm going to pretend that the indicator should actually be here, because to get the 0 reading there it has sagged down, and again here it's sagging down, so the reading should actually be more like here. If I now draw that on, it's clear to see that there is actually a slight error in the angular measurement. And why is that significant? Well, because the purpose of this operation was to set the angle of the spindle. And in doing so, I had created this reference in blue by taking the facing cut. Well, of course, that reference still stands, but the way in which I'm measuring it means that I'm actually incurring an error in my readings. So when I get 0, 0, there is actually this very slight effect due to the bars going in the same direction. This topic of bar sag is the most complicated one in this video, and therefore I believe it deserves a brief conclusion. On the one hand, yes, there are errors. Clearly, the weight of the indicator, the stiffness of the bar and the effects of gravity all add up to give a downward action, and that will give you errors that you can't necessarily see in what you're doing. On the other hand, how big are those errors? It was suggested that perhaps there was nothing wrong with the setup originally, and this 7 thou angular error that I surface ground out was actually just the bar sag. Perhaps I had 7 thou worth of bar sag and I've ended up just grinding this to account for the bar sag and I shouldn't have done it. Perhaps it was also suggested that because of all this bar sag you don't know what you're measuring and therefore it wasn't worth doing in the first place. Personally, I think both those comments are wrong. The amount of bar sag is, I believe, in the magnitude of half a thou at the most, and therefore is not the cause of the 7 thou error, and it does get you to within half a thou of a very good setup. So would I do the same again? Yes, but perhaps there's a few modifications that could be made. A stiffer bar, or a larger bar, or even better, mount the indicator directly to the spindle so there's no bar. Topic number 3 is that of setting the angle of the top slide, which I did using the Joe Pajinski method of using an indicator across the tailstock. Here's a brief clip. I am now going to bring the cross slide in until my dial indicator reads 0. This happens to be a 2 micron dial indicator and that's on 0. And while I'm here, I'm going to look up to the digital readout and I'm going to 0 the x-axis. Turning back to the top slide, I am now going to construct this 50mm length. Now this is 2mm per turn, so I'm going to do 25 turns. 24, 25. Back to 0. So I have now moved the needle of the indicator from here to here, and all that remains is to come in with the cross slide now and see if this number adds up. If this is truly flat, the start point's correct, and I've moved exactly 50mm at 7.125 degrees, I should be left with a drop of 6.201mm. So in goes the cross slide. and a quick look up to the digital readout. Oh, I'm exactly right. Now, a while back I had actually used a sine bar to demonstrate the setting of a similar type of angle. That was done on the Myford lathe, and it was done using a sine bar and slip gauges against the back of a chuck, and then clocking the angle of the sine bar. Now, a bit of a discussion was had in the comments around which method would be better. Well, let's have a closer look. So to go down the sine bar route, the first thing to do is say, well, what reference am I going to work off? You could work off a reference surface like this that's actually been machined, which would be my preference, or you could again work off the tailstock. And what would this look like? Well, perhaps you'd have a sine bar here, some slip gauges in there, and then somehow you've got to create a square to clock across, so you would have to have something like this. That has given you your angle here. Equally, you could take the slip gauges and the sine bar and set them on the tailstock. Now, the downsides of the sine bar have already been illustrated. Firstly, paraphernalia. You've got to go hunting for all your bits and pieces, assuming you have them in the first place. And secondly, once you've got them, you've then got to try and defy gravity in holding them up. And we have already discussed gravity enough for one video. So paraphernalia and setting up is one consideration. How are you going to get the sine bar here? Well, you've probably got to bring the saddle over and then build something up, or you've got to put the saddle under here, build something up underneath. Those are considerations, but you do get a good sine bar, and let's say you have a face you've machined, a sine bar, accurate slip gauges. That is probably unbeatable as far as accuracy goes, because there are going to be errors in measuring on a round surface. There are going to be errors in the tailstock's alignment, and as pointed out in the comments, you might incur errors between dialing it to 0 and then trying to replicate the 0 reading here. More error points potentially. The beauty of the tailstock method is that all you needed was the DTI, which typically you would already have out anyway, whereas all this is extra. Was I going to do another one tomorrow? I think I'd work off the tailstock quill again. Purely for the fact the indicator's already there and you don't have to do all this messing around with all kind of bits. Yes, okay, that probably is the most accurate. Worth bearing in mind, and depending on what work you're doing, that may be more suitable. However, one big thing to mention in all of this, whether you work off here or here, you're probably clocking across 100mm, 4 inches, and the actual taper I'm going to be machining, and even the top slide travel, is considerably less than that. So even if you can only get within a thou over whatever method you pick, the taper is probably going to be smaller than that. So in the case of the one I'm doing, it's about 14mm long, so it's significantly smaller, therefore the error is significantly less as actually exists on the surface. Point number 4 was raised by quite a few people, and I'm going to try and answer this fairly quickly. Before I begin, let's have a look at what I said in the video. So there is an error in the spindle this way on. Now, what could contribute to that? Well, obviously the bore to spindle relationship is important. The flange face to post relationship is important. I already know that this is in the clear because I've measured it for parallel, but equally the top of this slide versus the spindle relationship also matters. Now, the likelihood is all of these bits have a little bit of error that add up to the 7 thou I'm seeing. Now, I could go mad trying to find the error. What I'm actually going to do, because this is just a piece designed for this roll and this roll alone, I'm actually going to mark its rotational positioning so that it goes back in the same place. I'm going to mark the rotational positioning of the post so it all goes back in the same positions, and then I'm going to go to the surface grinder and I'm going to grind the correct angle on top of here, or should I say the corrected angle, to give me the correct spindle angle. So as a brief recap back here today, what I said stands. You're going to have a build-up of error in all these things, and you could go to town taking out the error in all these things. Because you've got so many things, you will probably still have an overall error. but certainly, let's say you could get very close if you were able to find out the angle this needed to be ground at, which isn't necessarily straightforward. You could regrind this. This would be ground parallel, this face would be ground perpendicular to the shaft, and you would check out the relationship between the centre bore of the tool post grinder unit and the spindle, and hopefully that would be correct. So yes, let's say you were going to be setting the tool post grinder up once a week. That would be a good route to go down, because every time you just push it on, whatever angle and orientation everything happens to be at, you know you're going to get a square result. However, in this case, for a one-off setup, I felt that was slightly going down the road of making a project out of a project, and as you may well be aware, I don't need any help in doing that, so I look for opportunities to reduce the number of projects, and the quickest way to do this was to grind the top plate and just take the whole area out in one go. I have marked up the front, and so assuming the top slide is at a similar angle next time I happen to do some tool post grinding, if I align the marks I should get something like. So that is the brief answer. Yes, doing all this might be the proper route to go down if you are trying to produce a setup that can be replicated by anyone reasonably quickly, but it's making a project out of a project in this case, and I'm perfectly happy with the route I went down, which is to take the whole area out in one go. So hopefully that was of some value, and hopefully it shows that the process of leaving comments in the description can lead to further discussion topics, and in this case further videoing. Now, on the topic of comments and viewer interaction, I have had quite a few comments from this gentleman, and he's ended up sending me a book. For those of you interested in the idea of home workshop CNC, in this case milling, then I'm going to go as far as to say I would highly recommend this book. I don't, or so far haven't really got into the topic of home workshop CNC, but I do CNC at work, and what has impressed me about this book is he actually goes into a lot of detail on topics that you have to consider in proper industrial machining but often get overlooked in the home environment. So for those of you interested in home workshop CNC milling, this is the book, and if you are interested, then I suggest you take it further. Apart from that, I'll say thank you for watching. I hope you found this interesting, and see you on the next video.